Let's take a look at finding the derivative of exponential functions that have bases other than e. But let's start with reviewing what we already know about finding the derivative of e to a power. So for finding the derivative in terms of x of e to the u, that gives us e to the u, so here's our chain rule coming in, multiplied by the derivative of the power, or we could write that as du. So the derivative of e to the u is du. And now we're going to look at exponential functions that have bases other than e. And of course we're going to want to know if there are any similarities or differences between those. So let's start by finding the derivative of y equal to 2x, and you can see from the instructions we're going to use logarithmic differentiation to determine that. Now, logarithmic differentiation is simply a process by which we're going to take the log of both sides, and we can use any base that we want. I'm going to use base e, so I'm going to take the natural log of both sides. And the advantage of, or the reason we want to take the log of both sides is because that allows us to bring the power of x down using log properties. So here we go. In problem number 1, I'm going to take the ln of both sides, so that would be the first step of the process. So I get ln of y. Using a log property, I can bring the exponent down, and I'll have x times the ln of 2. So I kind of did two steps in that process. I took ln of 2 to the x, and then the second step would be to use the log property to bring the power down. The second step of the process is now we want to find the derivative, so I'm going to take the derivative of the right-hand side, and the function that we currently now have over here, instead of being exponential, it's a power function because it's a coefficient multiplied by x, and in fact it's a linear function. The derivative, if you think of a function like 5x, the derivative of 5x is 5, and the derivative of pi x is pi. So the derivative of ln of 2 multiplied by x is simply the ln of 2. On the left-hand side, when we find the derivative of the ln of y, we're going to use the chain rule, so we get y prime over y. Now keep in mind what our goal is. Our goal is to find the derivative. Well, we have y prime sitting right here. We just need it by itself. So to get y prime by itself, I'll multiply both sides by y, so that gives me ln of 2 multiplied by y. So now we have the derivative. However, it's not in terms of x. The original problem was in terms of x, so I can substitute in place of y its equivalent, which is 2 to the x, and so y prime, the derivative, is equal to the ln of 2 multiplied by 2 to the x. And so we have the derivative, and we found that using logarithmic differentiation. All right, let's take a look at problem number 2, and we're going to follow the same process. So I'm going to take the ln of both sides in order to bring the power down. So I get ln of y is equal to 3x times the ln of 2. There's my log. That's my algebra step. Now I'm going to take the derivative of both sides. The derivative of ln of y is y prime over y. On the right-hand side, the derivative of 3x ln of 2, again, it is a linear function or a power function. So I'm going to get 3 ln of 2 because I could rewrite that as 3 ln of 2 multiplied by x, and 3 ln of 2 is just a number. It's the coefficient of x. And so that's why the derivative is just that number. Okay, let me get rid of that. We want the derivative, so we want y prime by itself, so I'm going to multiply both sides by y, and that gives me 3 ln of 2 multiplied by y, and just like I did in the first problem, I want this in terms of x, so I'm going to replace the y. So in this problem, y prime, or the derivative, is equal to 3 ln of 2 multiplied by the original function 2 to the 3x. And then we're going to apply the process one more time to the problem, and then we're going to take a look and see if we can see any patterns. Step 1, take the ln of both sides. Again, that's my algebra step. I'm going to apply the property. Take the derivative of both sides, just like I did before. 4x cubed times the ln of 2. Multiply both sides by y. 4x cubed ln of 2 all multiplied by y. Substitute in the original because that's its equivalent, and I get, let's go back to red so they're all the same, y prime is equal to, or the derivative is 4x cubed ln of 2 multiplied by 2 to the x to the fourth. That's the original function. All right, now let's take a look at all three of these, and let's see if I can get them all in one screen. Notice that in every derivative, one thing that they have in common is that in all three cases, we have the ln of the base. And in this case, in all three of these examples, the base was 2. So I think we can say that part of our derivative, if we come over here and we're looking for a pattern, is going to be to take, and I'm purposely writing this in the back, you'll see in just a second why. I'm going to have ln of the base, because they have that in common. The next thing that we should or can notice that they have in common is that every problem contains the original function. So if we come over here and generalize that, then we would say then the derivative of a to the u is going to be a to the u. And then the last thing that we can detect by looking at each pattern, let's change to this, let's change to a green. Notice the derivative of 3x is 3. There's the derivative of the power. Notice that in the last example, the derivative of x to the fourth is 4x cubed. And even in the first example, if the power, let me circle that here, if the power is x, the derivative of x is just an understood 1 that could be in the front. So in every case, we have the derivative of the power is u, so we end up with du. So what I wanted you to see is that the pattern is the same as finding the derivative of e to the u. It's always going to be the base to the power times the derivative of the power multiplied by the ln of the base. Well, if you think about it, I could actually write this as ln of e, and the ln of e is 1, so it's unnecessary, but it still follows the pattern. So we don't really have to think about it when we're finding the derivative in base e. All right, let's take a look at how we're going to apply this. And I'd like to start with problem number 5 first. In problem number 5, when you're finding a derivative, remember you're always looking for the right tool for the right job. And if you take a look at problem number 5, the first thing I hope you notice is that this is a product. So we're going to need the product rule. And then while you're doing the product rule, this product is comprised of a power function, and the power function is x to the fourth, and it's also comprised of an exponential function, which is 4 to the x. So these are all of the derivative tools that we're going to need to find the derivative here. So when I find the derivative, I get y prime, again remember product rule, the first function, times the derivative of the second. And when we're finding the derivative of the second function, now we need our exponential rule that we just learned. So we said it's going to be a to the u, so that's the function itself, multiplied by the derivative of the function. Well, the derivative of x in this case is just 1, so I don't have to write that. And then multiplied by ln of the base, which in this case the base is 4. So that's the first times the derivative of the second, plus the second term, which is 4 to the x, multiplied by the derivative of the first, which is 4x cubed. Now there is a little bit of cleaning that we could do here. I could factor, here are my two terms, I could factor a 4 to the x out of both terms. I could also factor an x cubed out of both terms. And in the first term, in this one, that would leave me with, let's see, if I'm factoring out x cubed, that will leave me with x. The 4 to the x is factored out, comes the ln of 4. And in the second term, if I factor out a 4 to the x and I factor out an x cubed, then I will have a 4 left over in there. If I did that correctly, I think I did x cubed, x. Okay? So within that problem we used, I'll highlight for you where we used the new rule that we just learned, the derivative of an exponential function. It's right in there in the midst of the product rule. Now I'd like to take a look at problem number 4, and then I'll probably just talk about problems 6 and 7. Let me clear the board here. In problem number 4, there's some things that I want you to notice here. First of all, this function is not a power function. Some students want to try to use the power rule here and do silly things, but this is not a power function, because a power function is when you have a variable base. The power rule is when you have a variable base to a fixed number power. And what I mean by that is x squared, x to the first, x cubed. Those are power functions. This is definitely not a power function because this power is not a fixed number. It's also not an exponential function. An exponential function is a function of the form a b to the x. In other words, it is a fixed number base raised to a variable power. And so when you look at the base, secant x is not a fixed number. So it's not a power function, it's not an exponential function, so I don't use those rules to find the derivative. So what am I going to use? Well, one thing that would be helpful here is if I could bring this power of cosine x down, and the only algebraic tool that I have to do that is a logarithm. So again, I could use any base that I want, but it's most common that people use natural log. So I'm going to take the ln of both sides. This is my algebra step. I'm going to do what I did on the other page, which is to use the property and bring the power down. So I have cosine of x multiplied by ln of secant x. And that's just the algebra step to bring that power down. Now once I do that, I have a product. On the left-hand side, the derivative of the ln of y is y prime over y. On the right-hand side, I'm going to have a product, so I have the first function times the derivative of the second function, and the derivative of the ln of secant x is u prime. So I get secant x tangent x over u. That was the first times the derivative of the second, plus the second ln of secant x times the derivative of the first, and the derivative of cosine is negative sine x. So cleaning that up, I have y prime is equal to secant divides out with secant. Remember that tangent is sine over cosine, so if I multiply cosine times sine over cosine, I'm going to get sine x plus, actually I'm going to go ahead and move the sine x in front, doesn't really matter. So I'll have sine x, so that's left over from the first term, minus sine x multiplied by ln of secant x, put that in parentheses, and then I'm going to multiply this y to the other side, except I'm going to write it, or replace it just like I did before. So sine x minus sine x times the ln of secant x multiplied by, replacing the y with the original function, secant x raised to the cosine of x. Now I know that may seem pretty difficult, but it really is not if you're careful. It just involves recognizing the pre-calculus and really just being careful in your work, remembering to multiply both sides by y and replace it. So that's problem number 4. And notice problem number 4 did not use our new rule. Remember, when you're finding derivatives, it's very important to use the right tool for the right job. In other words, the right derivative rule for the right function. And we're not going to do numbers 6 and 7. We're just going to talk about what you would do and what would be involved. I'm going to clear the board again. In problem number 6, the first thing, and it would be pretty much in this order, is the quotient rule, unless you rewrote it. You could rewrite this problem and make it a product rule if you wanted to. But from first appearances, I see the quotient rule. Then the next thing that I see in the numerator, I see the chain rule. And in the midst of that chain rule, I'm going to need the power rule. And then in the denominator, I see trig. And in the midst of that trig, I see the power rule, because when I take the derivative of the angle, which is 4x, I'm going to need the power rule. So in this case, we have a series of various rules that we have to apply in the correct order to make it happen. And then finally, number 7 is a little bit of a tricky function. If you play your cards right, you won't have to do very much work. Many students would say, well, this needs the quotient rule, and then you have to do e to a power, and then power rule. But if you look before you leap, hopefully, you'll notice that e and ln are inverse functions, so they undo each other, leaving me with 2x in the numerator and a 2x in the denominator, which is equal to 1, and the derivative of 1 is 0. So always look for simple ways to do the problem. Hopefully you find this video helpful on finding the derivative of exponential functions.